All right, guys, we're going to get started. My name's Howard. This is Life of a Mechanical Engineer. It's kind of late, so thanks for sticking around so long. I know after this I'm going to get some dinner. So quick overview of what we're going to do today. We're going to have a brief history of mechanical engineering, some relevant coursework that I've taken and that you can find in some classes, some typical job prospects. Sprinkled throughout, there's going to be some application of knowledge, some life stories, and most importantly, we have prizes today. So if you participate, you could go home with something else. And I hope I don't go home with it because I don't want to keep carrying it all day. So who am I? I'm Howard. This is me at several different things at FRC Robotics. I am a scholarship winner. I've done a lot of things around the field, for the field. I've gone to China. I've ran robotics competitions at my own university. So I'm pretty familiar with the world of FRC. And it's because of FRC I actually went to school for engineering. So again, this is like my 13th year in FRC. I've been doing this for almost as long as some of you have been alive now. I chair different committees. One of them is the off-season committee for New Jersey, Pennsylvania, and Delaware. I run the New York City Roborama off-season that some of you were able to participate in. Scholarship winner again. I have a bachelor's in mechanical engineering, and I have a master's in systems engineering. And I get this question a lot. I do not work for FRC. So, sorry guys, I don't work there. So, let's actually dig into mechanical engineering and kind of the history of mechanical engineering. So, long time ago, Greek and Romans, they were doing things that we never thought were possible. They built aqueducts, they built roads, and they did it with tools at that time. They didn't even have the modern day tools that we do, and we still seem to mess it up. But a lot of the principles can really go back to the 6 simple machines: the wedge, the inclined plane, a wheel with axle, lever, and balance scale. If you take any like intro to physics class or mechanics class, you're going to learn all about these. If you want to learn about them, if you want, we can talk later, but that's for another day. Water and windmills, it really allowed humanity to kind of harness the power of nature. So even in Iraq and in Europe, we had windmills to try to catch the wind and turn wheels and and crush grain into finer pieces, make flour. We have water windmills that, you have a river, you put a wheel next to it, you start to turn the wheel from the river, and it turns some other things, and it helps you take some, the power of nature and harness it for your own usage. These things, they date back to 300 BCE, we were doing it. And even as recently as 1657, the first pendulum clock. We kind of live in a society right now where you ask somebody what time it is, you take out your phone, and they'll tell you it's a time. And you pull out your phone, and it's like maybe a minute, maybe 2 minutes at the most, different from one another. But way back when, people had to keep times. Like, I'm going to meet you at noon. Well, when is that? And clocks, you have to wind them up, and they could be off by 15 minutes in one direction. So theoretically, you could be off by a whole half hour. So they created this pendulum clock using the swing of Earth. And it was the first time that we actually had reliable timekeeping instead of having clocks drift over time. So fast forward to kind of here in America. In 1880, we founded the American Society of Mechanical Engineers right here in New York. It was a response to a bunch of steam boiler failures. Now these steam boilers, people would make it, and there wasn't really any codes or standards. And they would kind of just, put it in a kiln, make it, and oh, now here's a steam boiler. And these would explode because they would have faulty designs, they would have faulty construction work. And a lot of people came together and said, oh, we got to make this up. We got to standardize some codes and standards so that everyone is playing by the same thing. So if I have, place A make a steam pipe and place B make a steam engine, they're going to fit into one another. And then the Industrial Revolution. The Industrial Revolution really took off in Europe, but it wasn't until a man by the name of Francis Cobalt Lowell, who memorized the design of a textile machine when he came from Britain to the US, and then he built a machine based off his memorization in Boston and created textile factories in Boston, and that really kicked off the Industrial Revolution in 1810. So that was a brief history, but what is mechanical engineering? It's really a combination of physics, math, material science, design, analyze, manufacture, and maintain mechanical systems. That's your pretty one-sentence definition that some people really like. But really the field of mechanical engineering is very, very broad, and it expands over time, right? 100 years ago, no one knew what nanotechnology was. No one knew what mechatronics were. Aerospace technology, we could barely get a plane off the ground at Kitty Hawk. So this is kind of really expanded, and there's many, many areas of active research. Metallurgy, biomedical, composites, MEMS, it's pronounced MEMS, not memes, sorry kids. It stands for microelectrical mechanical systems. So some relevant coursework. I'm not going to talk about every single class that you might take, but I'm just going to talk about a few brief different subjects. So the first one, maths, which is kind of a very British way of talking about mathematics. I've never used a differential equation since college, and you have to learn Calc 1, Calc 2, Calc 3, Calc 4, and depending on where you go, they have different pretty names for it, like multivariate calculus, differential calculus, integral, derivative. It's really all the same thing. You have to take all 4 of them. But really, if you want to go into a STEM degree, you want to go be an engineer, you really do need to kind of pay attention to these classes, because I always considered studying for math kind of like studying for all of my other classes. If I could do the Laplace, or if I could do a differential, it's going to show up later in my other classes. So just learn it then, learn it right, and it's going to help you later on your other classes, because we all know when you get a grade, you take a test, you have to solve the problem. You can't solve the problem, you don't get points. So being on the other side of this now, when I try to help teach and help kids kind of remember how to do calculus, the majority of mistakes is not calculus. The majority of mistakes is algebra and just being diligent and carrying from step to step. So just recognize calculus is usually not the problem, it's algebra. And number sense is more important than memorizing. If you do a problem and you're starting to realize that the answer that you have does not make physical sense, like you have a number that's so big, it's more than the number of atoms in the universe, you know you're doing something wrong. So number sense is very important. Like if you know it's a percentage, 0 to 100, and if it's over 100, you mean the number is getting bigger. If you have a probability that's like 2.5, that shouldn't be possible because it's 0 to 1. So math, it is important. It doesn't exactly go away until you graduate. So statics, a lot of people call this engineering physics. It's really just applied engineering and applied physics. This is kind of like a sample problem that you might see. Something that I try to teach kids is whenever you get a problem, the first thing you do is you read the problem twice before you do anything else. And then you start to write your givens, you start to write your assumptions. And just a quick question here. So this is the first time, this is the audit, you can win a prize now. You get this problem, how many equations can you use? And anyone? Shout a number. So,
As many as we need.
not exactly. Yeah?
2.
There's more equations than just 2. Yeah?
4.
4 equations. Do you know what 4 they are?
No.
See me after class. So we all kind of know like there's different ways of looking at things. You can look at it in an X, a Y, and a Z plane. So you can have all the forces in the X, all of the forces in the Y, then all the forces in the Z, and then all the forces put together makes your 4 equations. So in any system, you always have a minimum of 4 equations. So sometimes you'll like set up a problem like, oh, there's like so many things I don't know. It's, well, break it down into 4 equations and you can pretty much solve anything you want. Design machine components. This is really just the application of simple machines. Now you're just kind of adding a little bit onto it. So an example might be you have a bunch of gears. Gears are really just levers, just put into a really nice pretty package with fractions. And it's kind of also the idea of you have an output force that you want. You want to always have 100 newtons of force. Well, what part will be able to withstand 100 newtons of force? And design and machine components can help you figure that out. There's a fun story about my design and machine components class. We had an exam. It had 3 questions on it. And on the 3rd question, the guy said, you need to look into your book at the table A13 and find the equation to use. And if you don't have the book, I printed out table A13. I have it right here in the front for you to use. And just in case, let's read the question. And he highlighted the exact words of the equation you needed to find. And we took the exam. The exam comes back, and he says, I don't understand. I feel like I've read the problem to you. I gave you the table. I said what equation to use. But how come half of you couldn't get it right? And it's not just one thing to know the equation. You also have to know how to use it. So it's just always incredible to I think back to that. I got it right. I felt good about myself. But half the class got it wrong when he kind of handed you the equation and people couldn't do it. So F equals ma, you guys kind of understand. You've heard of it at least. You know, if you just plug in things, eventually you kind of get something out of it. Thermal engineering. It's really only helpful if you're going into some heat transfer or related areas. I've only had to look at a steam table once since college. I like to call steam tables like where's Waldo, like where's the number I want to find. Nowadays they have online steam tables, which is a lot easier because you can just kind of, you know, say computer, I want, you know, this at this value. But the thing that you really need to know is just general principles of like a PV diagram, or as things heat up, they tend to expand. And it's just keeping those in the back of your mind. You're working on a project, you know, maybe you're working on a drivetrain. Well, your drivetrain's working at 100% duty cycle. It's working all the time. And then you hit the brakes and you go from like 100 miles an hour to 0. Well, you're going to create heat. Well, what is that heat going to do down the chain? And knowing some thermal kind of helps you understand, well, if you're heating up your brakes and you're heating up your engine, you're doing it, well, the oil in your engine might start to boil because the engine's heating up. And the oil's in the engine. So, you know, heat's gotta go somewhere. Next class is probability and statistics. I use this almost every week, reliability analysis. One of the most frequent questions I get from a customer is, how sure are you? I want this to work 99% of the time. And it's like, 99, like, how do you quantify that? Well, what you can use is a previous set of data to get a probabilistic outcome, but you can never be certain. And I kind of relate this back to, you have a box of matches, and you want to be sure that that box of matches is going to light. Well, the only way you can be sure that that match is going to work is by lighting the match. Okay, so I light the match. Okay, cool, the match works. Well, that kind of defeats the purpose because now you can't use that match anymore. So what can you do to make sure that a match is going to work? Well, I can take a couple of samples from the matchbox, light them up, see if they work, and then what does that tell me about the next match? So, you know, with every successful match that lights up, I'm more and more confident that the next one is going to work. But I can never be fully certain because there may always be some stray case. Kind of the partner to that is modeling and simulation. I use this constantly. If you model something, you could avoid breaking something really expensive. Just the other day, I got a part that was worth $200,000, and they wouldn't let me even touch it until the model proved that it would work. And the model is what helped me greenlight that project from our company leadership. And that model, let's say, you know, it didn't work. Like, we didn't do the model and it didn't work. Well, that would be $200,000 to write off. And I don't know about you, but I could buy a small house for $200,000. The other thing to know about modeling and simulation is you don't need to know how to code everything in the world, but knowing some basic code is very helpful. If you want to run a quick report based off something and you know a couple of things about how to code, you can just write a script, come back to it later, pick it up. Also, learning CAD is very useful. So you get a part or you get a design and then you want to look at it. Well, you know, I can hold my phone in my hands, but how do I hold a part on a computer? So not necessarily, you know, make a whole beautiful, you know, gear train, drive train, but knowing how to observe parts and look at parts is really, really helpful. Material science, this was like the hardest class I took at university. Has almost zero relationship to anything that I did. But there are some kind of principles to remember, like what things are magnetic, you know, strength of properties, manufacturing properties. Anyone hear of Teflon? Like a Teflon pan or a Teflon slider? Well, one of the material properties of Teflon is it's self-lubricating. So you don't have to put any like oil or lubricant onto it, it lubricates itself. So, and that's very, very useful, even in applications of competition robotics, where you might have things that are sliding next to one another. You don't want there to be friction, you want it to glide. So some people will use Teflon because then they don't need really any upkeep.
How does it lubricate itself?
We'll talk about that later. So unless you're going into a material or metallurgical field, it's not super relevant, but it's good things to keep in the back of your mind. Manufacturing process and system. This was, I thought, a very fun class, except for the ladder logic, which it's useful to understand, but unless you're doing something with ladder logic in your life, you will never need to know this ever. A lot of people, they look at this and they're like, where the hell did this come from? So some other things about manufacturing process is that, let's say you go to the store and you want to buy a Coca-Cola. Well, you get it out of a can or you get it out of a bottle, but there's no one on this planet that's going at the Coke factory pouring Coke syrup into a can or pouring Coke syrup into a bottle. We automate this process. We have machines that do this for us. And it's all automatic. And someone's got to figure out, well, how do I design this whole assembly line? How do I get the product into the bottle? How do I get the bottle cleaned and ready? And that's this whole idea of manufacturing process of you have something that happens, it triggers the next thing, which triggers the next thing, which triggers the next thing. And you can speed it up, you can speed it down, you can ramp up, ramp down, you can turn it off. And then there's this whole active field of research and companies that just do complete automation. There's one of my favorites is there's a automation conference in Germany every year, and there's like a whole section of it, like 1/8 of it, just broken out into sushi making factories, and it's really, really cool to watch. You can find it on YouTube if you want. So some common job prospects. I think the number one that I always hear is CAD or computer aided design. I have like 3, 4, 5 friends that the only thing they do is work in SolidWorks, work in Inventor, and just create a design. They love it. HVAC, think of it as heating and cooling. This building has a heating and cooling system. Someone has to design that product that gets the heat or gets the air, or whatever, to a location and then install it. Technical sales, let's say you want to buy a part for something. Well, someone needs to know how that part works. So there has to be this interface between a person selling the part and some type of engineer or some type of knowledge person explaining the part. Automation and industrial design, we kind of just spoke about that. Powertrain, cars and vehicles. This is a huge area of active research right now. Everyone, is hearing about electric cars and electrify. The biggest problem right now with electric cars isn't the car. It isn't, the roads. It's the battery. And it's how do I make the engine more efficient so I can go further, I can get more miles out of it. Aerospace engineer, self-explanatory. Systems engineer. So a lot of people think systems engineer is like a computer backend. That is, I guess, one element of systems engineering. But systems engineering is really kind of more of the customer-facing side of engineering of, I want something. Well, how do you want it? I have to listen to the voice of the customer. I have to somehow get some needs and desires out of them, translate that into some type of requirement that we can kind of test to, then from the requirements create some type of spec, and then kind of go back up the systems V of, well, did what I spec meet my requirement? Did what I build meet what my customer desired? Did what my customer desire actually fit the problem overall? And they talk about the systems engineering V. And this could be like its whole own lecture. Instrumentation engineer, think of this as like your codes and standards. Let's say you have an antenna and it needs to radiate at some power level. Well, someone's got to sit there and be like, yeah, that is a safe number, or this is a number that we can experiment at. R&D, research and development. There are tons of places that do research and development on different mechanical products. So your phone, right? Someone had to design this phone. Someone had to create the shape of this. Someone had to think about, well, where am I going to put each and every single part on the phone? There's no such thing as like a phone engineer. It's always, a bunch of different teams trying to come together. And there are many, many, different job prospects, but these are just a few that I pulled out. So, comments from mechanical engineers. These are real world quotes from mechanical engineers. Anyone can learn a tool. Learning how to think and approach is the key. I can teach a kindergartner really how to do calculus, but to teach them to understand what it means, that's a big thing. I never understood how much I'd be using CAD. I swear, I work with another mechanical engineer, and she is on CAD 24/7. Every time I go to her desk, she has these 3 giant monitors that just doing CAD. I don't know how she does it. It's like she's being beamed with light from CAD. You don't need to remember everything, you just need to know where to find the information. So when I was looking at that heat transfer problem I was solving at work, I don't memorize steam tables, I don't memorize equations. I just, let me remember how to find this. Let me go online and get the steam table, let me go online and find the equation. And then I remember a little bit, and then I kind of just did it and figured out what the numbers I needed were. Until you prove the design, it can be hard to find buy-in. To kind of go back to that $200,000 part, until I could prove that design, no one's going to buy that $200,000 part for me. They could buy it, it could be not the thing that we need, and then we're down 200. Follow process, but don't get bogged down by it. A lot of companies have engineering design process, and they have it for a reason, because they don't want people to design something that's impossible to make. They also have a lot of lessons learned that they try to avoid in the future. And I find that personally, process can be very painful, but there is a reason for a lot of them to exist. So next is kind of the most interactive part of the presentation. We're going to talk about the 10 greatest feats of engineering in the 20th century from ASME, the American Society of Mechanical Engineering. When I started in college, they actually did the same thing with me, and I won this. I actually named all 10 of them, and I won a prize.
What was the prize?
It was a solid state hard drive at the time. It was like $200.
Oh,
Yeah.
okay.
I do not have $200, sorry guys. I do still have it, yeah.
Oh.
Alright, so number 10, first, actually, before we do this, anyone have any ideas what they might be? Yeah?
Computer chips that are very small but very powerful.
Could be. Anyone else?
Drones maybe.
Drones, okay. Anyone else?
An engine?
I'm sorry?
An engine?
Okay.
LEDs?
LEDs, okay. Was that what, did you have another one? No?
Maybe AI.
AI? So remember, 20th century, and ironically 20th century doesn't mean 2000, it means 1900 to 2000. Yeah?
Digital clocks?
Digital clocks, that's a personal favorite to me because I hate reading a clock. Yeah?
Film cameras?
Film cameras, okay.
Heating and cooling systems?
Heating and cooling systems, okay.
Semiconductors.
Semiconductors, yeah, that's a big thing. All right, any other guesses before we move on? All right, we'll see how good some of you are. Now, we're gonna play a little game. There's gonna be a little bit of clues, and kind of the first person to kind of jump out and tell it to me will win. If you win a prize, see me after class. Some of the prizes are real infinite recharge volunteer shirts.
Oh.
Other prizes include a lapel pin that I make. So, controlled by hands and feet, I would be nothing without a street. I have a trunk and can be sold as junk. Just say it.
Automobile?
Sorry?
Automobile?
Alright, see me after class. It is automobile. Alright, next one. You fly to Japan, you bought a pair of shoes, a shirt, a pair of socks, and got lunch after departing. What did you buy first?
Ticket.
It might be a ticket, but what is the engineering feat?
A plane ticket.
A plane ticket. So the answer is an airplane.
You didn't buy it though.
I hope you did.
So the idea was to get to the airplane.
But maybe you just bought an
Air
airplane.
conditioning.
Air conditioning, yes. Ironically, heat is considered a necessity, but in the summer when it's like 105, air conditioning is not considered a necessity. Please write to your local congressmen and politicians about that. I don't know if I could live without air conditioning. All right. Why buildings shouldn't collapse and why everything is moving to USB-C. This one's a little bit harder.
Steel.
I'm sorry?
The type of metal.
No. How about I tell you the story that goes with this first and then see if anyone kind of figures it out. So everything's moving to USB-C because the European Union announced a policy to reduce electronic waste. When they reduce electronic waste, a lot of different companies settled on the USB-C form factor, which pushed everyone to standardize and harmonize to one form factor, which then allowed them to standardize ports, meaning they need less ports, and make smaller devices. Any clue, any idea? We actually talked about this early in the presentation. It was the reason why ASME was formed.
Standardized parts.
Close.
Steam boiler.
I'm sorry?
Does it have something to do with the steam boiler?
It does have something to do with the steam boiler, but it's not the steam boiler. Kano, you're so close. You have one of the words.
Standardized sizes?
Steam engines?
No. Standardized what?
Sizes?
You're so close, but you're not there just yet.
Standardized chargers?
No. Sorry.
Replaceable parts?
It's not a physical thing. It's a written thing.
Is it a type of rule?
I'm sorry?
Is it a type of rule?
It's very, very close to a rule.
Is it code?
I'm sorry? Some.
Code?
It's codes and standards. Codes and standards.
Ah, I get
Yeah.
it now.
So USB is a standard. You know, buildings have codes. So you want to build a building, right? You know, you can't just put bricks down. You got to get you might have to get a permit. You might have to apply adhere to some building standards, some codes, and sometimes you see signs. Occupancy of this room shall not exceed, and those are because there are fire standards and fire codes that you have to abide by. So see me after class. All right, number 6. This is more of a image, if anyone can figure out what's number 6. Yes? There's something that could be a little more specific.
Engineering physics?
I'm sorry?
Engineering physics?
Not exactly. We were using a lot of this to help create vaccines.
Bio. That has something to do with bio, right? Bio.
Yes, it has something to do with bio. You're so close.
Bioengineering.
Bioengineering. See me after class. So bioengineering is one of the biggest outcomes out of mechanical engineering. The idea of taking, a design and being able to create biologics that can help people, like steroids. People use steroids to treat different problems. People use vaccines to treat different problems. All right, number 5. This is a whole story. So there's one major company that does this idea, and their origin story became a movie. And it started with $1 million from them participating in the MIT blackjack team. The blackjack team was a bunch of mathematicians at MIT that would go to Las Vegas and count cards in their head. And then within 14 years from them starting this company, their annual revenue was over 100 million. So it's a good idea. So this is another thing that was mentioned earlier in the presentation. The movie was called 21.
Never watched it.
Probability and statistics had nothing to do with the company, ironically. I have it installed on my computer.
Scratch?
No. CAD, yes, CAD. So the name of the company is called SolidWorks. And their origin story is their founder was part of the MIT blackjack team and used some of his winnings to found this company after they started creating the thing called the Black Book, which is if they catch you cheating, you get entered into the Black Book and you can't gamble in Vegas anymore. So they take them all and they go to Atlantic City. All right, number 4. Mass chip shortage, and I'm not talking about Lay's.
Computers?
Not exactly. It's something more basic.
Semiconductors?
Yes, but no. It's not the actual semiconductor.
Silicon?
No. You have a... Are you going to say silicon?
No.
No. So this is the area of automation that really kind of helps us. Because we used to make semiconductors ourselves. You'd have like somebody there with a soldering iron and trying to put the chips together. But, I'm sorry?
Processors?
Not exactly. you take the chips and you make the processor. It's the idea of the creation of them.
Robot arms?
Robots.
Graphics card.
No, it's more basic.
Machining?
It's the machining with the card, or with the circuit. Maybe I'll just give this one to you guys. It's the integrated circuit mass production. And this is the huge problem that we have right now, trying to create a bunch of semiconductors, a bunch of chips. And ironically, one of the major companies, Taiwan Semiconductor, they're trying to make more chips. But to make more chips, they have to take the chips to build machines to make the chips. So it's almost like chicken and an egg. We take our current chips and use it to make more chips.
Is there an element?
I'm sorry?
Is there an element?
An element? What do you mean?
Like, is it copper?
No.
So they manipulate silicon to create different properties.
Okay.
And that's why it's a semiconductor. It's almost conductor. Number 3, this is a little harder. Originally nature or animal driven. Only recently have we harnessed this technology to magnify production, and it's what I'm going to be really using after this presentation. Yep.
Wait. Never mind.
Food engineering?
Very close, very close.
Knives?
We had knives for a while.
Agricultural?
Yes, agricultural mechanization.
Oh.
So think of like this whole area of New Jersey, New York, really was farmland. But as we've been able to kind of magnify our food output, we could kind of industrialize more. We could put more things here. New Jersey, like the town that I used to live in, used to pretty much be only farmland. Now it's much more suburban. So a lot of, I like to call little older people kind of reminisce about the days of when it used to be farmland, and now it's all like, cookie cutter homes. So it's only recently we've been really magnifying our food output so that we could feed everyone but still have enough space to live.
Have you heard of Elon Musk's offering to pay for world hunger?
Yeah, I have heard of it. I can't wait for him to pay. My bank account is always accepting money, by the way. So this is a little bit more graphical of what it's trying to do. So there are a bunch of different windmills, a turbine. Yep. I'm sorry?
Gears.
No.
Power generation?
Power generation, yes. It's this idea of harnessing power and being able to kind of use it and manipulate it to do whatever we want, right? We have engines and turbines. We can fly somewhere with an engine. We can capture the wind with these turbines and save it into a battery and use it later. The Hoover Dam, one of the greatest achievements that we've accomplished here in America. The dams, they create so much water buildup, so much weight of water, it actually changes the orbit of Earth. It makes days last longer or shorter by a very small amount. I think the Three Gorges Dam adds like 3 microseconds to each year in China. This one's also a very, very close to my heart one. Inspired generations to come. Without it, many people would never got into STEM. And let me tell you, we choose to do these things not because they're easy, but because they're hard. Thank you, Gene. None of you were alive for this, by the way. Except maybe Gene. What's up?
Aerospace technology?
It's very specific, but you're on the right track.
Reaching the moon?
There's a name for it. We've been to the moon many times.
Apollo moon landing?
The Apollo space program, one of the crowning achievements of NASA. It really did inspire, it challenged a nation to really kind of dig deep and aspire to do something. And I hope, the nation can come together for another great challenge like that.
I actually didn't have it. I thought you were referencing Woody's reference of that quote.
Woody was referencing Kennedy, yes. So just to review the top 10. A lot of these things, they really have changed life as we know it. I took an automobile, I took a bus to get here. I could take a plane to go everywhere I want. I love air conditioning. Codes and standards is why this building still exists. Bioengineering, I hope some of you got the vaccine, or almost all of you. CAD, integrated circuits, this computer, these projectors, they only exist because we can mass produce those circuits. I used to have these really great visions of some like electrical engineer hunched over trying to like solder onto this small board to create every single chip in my computer. That is not what happens. Agricultural, I'm hungry, you might be hungry. Power generation, I have, electricity right here in my computer. Apollo space program, a lot of my personal life mentors and engineers I've worked with, they only went into STEM because of the Apollo space program. So you may not realize it, but all these things, they may not just be exactly mechanical engineering, but mechanical engineering had a role to play in all of them. And with mechanical engineering, it doesn't mean you will only be doing mechanical engineering or only mechanical design. It really means that you got to take what you learn and be able to apply it in your everyday life. And that's kind of the hard part of, you might take 20 different classes, but in real life you may only need those 4 classes, but you don't know exactly what 4 classes those will be. So, too long, didn't listen. Mechanical engineers, they try to make a design to fit a problem. They may use tools such as CAD to help find a solution. Often you don't get to just build something unless there's a design first. I'll just tell it to you straight, most of what you learn in school is not relevant, but there are some principles, some little things that you can pull out that are helpful. If you know what you want to get into, it can definitely help to specialize in it. I have a lot of friends that like working with airplanes and cars, so they specialize in aerospace and automotive. I have one friend that does automation with Automation Direct. He makes a crap ton of money. He gets to go places. I'm jealous.
Wait. In what field is he in?
Automation.
Automation.
So you have a production line, and that production line might be in Iowa. Well, it broke down. Well, we can't fix it. Well, we got to send someone out to go fix it. Design follows a process, and the process exists because it's trying to learn from the mistakes or the lessons of the past. A lot of people may remember like the scientific theory method of like you hypothesize, then you design, then you analyze. A lot of companies have their own process where you need to do this, then do that, then do the other. And sometimes it's like, well, I gotta do this, and then I gotta do that. It's painful, but it's trying to learn from the lessons of the past. Some people just don't learn, unfortunately. And with that, one of my favorite things is just watching gears turn, and I'll take any other questions. Yes?
You really got all 10 of those on your first try, or
Oh, yeah. So what I did, because you don't work harder, you work smarter. I looked it up on my phone. I never said you couldn't do it. You guys just chose not to do it. So as soon as he put that challenge out, I asked him, are we allowed to use whatever we want? He's like, yeah, do whatever you want. So I pulled out my phone and I looked it up. Thank you. Without my phone, I think I would have gotten maybe 5, maybe 4.
More the most there.
Yeah?
You said your friend was in automation. What
Yeah.
field are you in?
So I graduated as a mechanical engineer. I worked as a mechanical engineer for maybe 1 or maybe 2 years, and then I moved into systems engineering, and then I got my master's in systems engineering. But the thing that I really think about mechanical engineering is it's really kind of the thought process. A mechanical engineer can be put on almost any team, and they'll be a good fit. Whereas if you maybe take an electrical, they may not be a great fit into a chemical problem. So I try to make my skills very broad. I try to keep learning. That way my skills are always applicable. And that's why I love doing computational robotics, because every so often you see a design or you see a solution, and you put it in the back of your brain, and then you wait for the time that you use it later. And that's happened to me several times, both at competition and at work. Because some of the kids are much smarter than me, and I'm like, wow, that was a really good idea. I'm going to remember that. And then I use it at work and say it's my idea, so people think I'm smarter than I really am. Any other questions?
Which universities are the best for mechanical engineering?
Stevens Institute of Technology is where I went, in Hoboken, right across the river. They're the birthplace of ASME. But that's kind of, you can go wherever you want. So here's the thing that I don't think people always understand about college and universities is no matter where you go, 1 + 1 is 2. No matter where you go, x times x is x squared. It's really kind of what you make out of learning and then taking the opportunity that's in front of you. Some places definitely have more opportunity than others. Some places definitely have better professor teachers than others, but it's really kind of you making the best of your opportunity. Is that a question or just a? Okay. Yeah.
Well, you just said that between getting your bachelor's and master's, you had a gap where you actually worked. Do you think that gap was really helpful?
Well, I worked the entire time. I got it while working full time, but it definitely is helpful having two separate disciplines to draw from, because there are times where I will think as a mechanical engineer at a problem, and sometimes I'll think as a systems engineer as a problem, and sometimes I'll use both of them. Sometimes I'll use none of them. But it's really helpful to have kind of that backbone to fall back on when you have a problem you've never seen before.
How easy is it to find a job after getting your bachelor's?
Engineering is always in demand. There's always going to be problems to solve. It's really just, you may not always want that exact job or want where that exact job is, and that's usually where the problem kind of lies, but there's always engineering jobs open. Like my company, we're hiring 50 engineers over the course of the next year.
Thank you.
What's your company?
L3 Harris Technologies. No, we do not take high school interns, sorry. I've been asked that many times.
On that topic, and software is really important to do an internship when you're in college. Is that true in your field as well?
I always think it's important to get real world skills. However, I also think it's really important to take a break. I personally wish I took a gap year after I graduated before I started working, because once you start working, your life is kind of dictated by holidays and vacation time. So if I were to leave my job, let's say, next year, I would definitely take a break before I start up a new job to go do things, which might be a little harder right now, but to kind of directly answer that question, yeah, it's always helpful to have an internship to show that you have work experience. And sometimes those internships turn into full hires. I've been lucky that every intern I've had has been a joy to work with, that I offer them a full hire position when they graduate. And none of them have taken it. They all go somewhere else. I'm so sad. The worst is one took it, but they went to a different site in New Jersey. And I'm like, damn it. So, again, to directly answer, it's important, but it's not gonna make or break you. I didn't do any internship, and I seem to turn out fine. I hope.
What things would you wish you were told when you first started studying for your bachelor's degree?
I actually wish I did do an internship, because it definitely would have helped me kind of narrow down exactly what, I don't say department or field of engineering, but kind of what location of engineering, if you will, that I like doing, because I really do like design work. Some people, they just work on CAD all day. I don't personally like that. I kind of like to do the adjacent part next to it of the specs and the requirements to give them to design. The other thing I would say is definitely take advantage of the opportunities that are in front of you. Sometimes you don't realize the opportunity is there until it's gone. I've been offered a lot of opportunities to do study abroad for basically free, and I kind of wish I did that. So there are things like that. So we got 5 more minutes. I'll be here at the well if you guys want to talk to me. If you want a prize, come on down. And if you didn't win a prize, come on down anyway. I got stuff to give away.